Welcome to Lecture 10, Section 2.4, Elementary Matrices. We are using the text Elementary Linear Algebra by Ron Larson's 7th edition Cengage Learning. This is Dr. Gilbert, Eyabi. Elementary matrix definition. An n by n matrix A is called an elementary matrix if it can be obtained from the identity matrix In by a single elementary row operation. So, A is an elementary matrix if A can be obtained from the identity matrix by a single elementary row operation. Let's look at an example. Okay, here is an example. Consider I3, the identity matrix 1 0 0 0 1 0 0 0 1. Now let's perform a single elementary operation on I3, switching rows 1 and 2. And that would give us the new matrix 0 1 0 1 0 0 0 0 1. This matrix created by this simple elementary operation is called an elementary matrix. It could have been 2 row 1 plus row 2, put the answer in row 2. That would have also resulted in an elementary matrix. Now let me go ahead and just show you a few things before we get back to the PowerPoint. Suppose A is this matrix defined. Look at the matrix very carefully. 0 2 1 1 negative 3 6 3 2 negative 1. I want to multiply the elementary matrix we just came up with, E times A. E on the left hand side. So EA, if you multiply that either manually or using your Math Studio on the iPad, you would get 1 negative 3 6 0 2 1 3 2 negative 1. Observe that E and EA have something in common. Basically, from A to EA, I have simply switched rows 1 and 2. That is interesting. So if I perform an elementary row operation on the identity matrix and get an elementary matrix E and multiply E on the left to any matrix, basically I would be performing that same elementary operation on the matrix A. And this is a very big thing in elementary matrices which I want you to remember. Now, one other thing I just want you to see, which we would revisit later. Suppose I set E times A to be a new matrix B. Then we observe that I did move from A to B through some elementary operations. So in the language of linear algebra, we say that A is row equivalent to B. So i.e., a matrix B is row equivalent to another matrix A, or vice versa. A is row equivalent to B if I can move from A to B by simple row operations. Theorem representing elementary row operations. Let E be the elementary matrix obtained by performing an elementary row operation on the identity matrix Im. If that same elementary row operation is performed on an n by n matrix A, then the resulting matrix is given by the product EA, what I just showed you a few seconds ago. So if I multiply E by A, I get EA. As a matter of fact, EA, I would have simply performed the exact same elementary operation on A, which I just performed on E. So if I can get a couple of E's to move A from what it is to a matrix it is row equivalent to, all I have to do is multiply on the left by E. Now let me give you the full definition of row equivalence. Let A and B be m by n matrices. We say that the matrix B is row equivalent to the matrix A if there exists a finite number of elementary matrices E1, E2, E3 right up to EK such that B equals EK, EK minus 1, E2, E1 times A. Now look at this very carefully and see what happens here. The first elementary matrix E1 is multiplied to A. That will cause the same elementary operation that we performed to get E1 to be performed on A. Then E2 is multiplied on this new matrix created, performing the same elementary operation that was performed on E2, and so on and so forth, and our final result is B. Let's check out another example which is probably more extensive than the first one we saw. Okay, find a sequence of elementary matrices that can be used to write A in row echelon form, not the reduced row echelon form, just the row echelon form. So we're going to go through this process, and while we're doing that, we will be creating a couple of elementary matrices. So here is A, our matrix, and it's a 3 by 4 matrix. So the identity matrix I3, we have that on the right hand side. So to create a row echelon form from the matrix A, I need a 1 in this top left hand position. So I switch rows 1 and 2. I perform the exact same operation on I3. So that gives me my E1. So that's the first elementary matrix. Now I need these two gone. I need a 0 in this position right here. So I multiply row 1 by -2, add that to row 3, and leave the answer in row 3. That is an elementary operation. I perform that same elementary operation on I3. Remember, I do not perform it on E1. I have to go back to the identity matrix to perform the elementary operation so that I can create elementary matrices. That creates A2. Now I need a 1 in this position, which I have. The next thing is I need a 1 in this position. I have a 2, so I do 1/3 row 3, leave the answer in row 3. That puts a 1 right there. I perform the same operation on I3. That gives me the elementary matrix A3. Now this is my row echelon form. Set this matrix, the new matrix that has been created, to be equal to B. So B equals this matrix. Now from what we saw before, basically the matrix B equals E3 times E2 times E1 times A. See the relationship between B and A? So we say that A is row equivalent to B, or B is row equivalent to A, because I can go from A to B through simple row operations. Now let me say a few things which I would reiterate when we get back to the slides. Suppose E1, E2, and E3 were invertible. As a matter of fact, let me just say that now, they are. All elementary matrices are invertible, and as a matter of fact, the inverse of an elementary matrix is also elementary. That's beautiful. Now, if E1, E2, E3 were invertible, now look right here, then we can multiply both sides of this equation by E1 inverse, E2 inverse, E3 inverse, that would get rid of E3, E2, E1, giving us E1 inverse, E2 inverse, E3 inverse times B equals A. I'm going to introduce you to a notion which we would see close to the end of this lecture. Observe that the matrix B is an upper triangular matrix. Upper triangular means that the only non-zero elements exist in the upper triangle of the matrix, i.e., if this is the main diagonal, the only non-zero element that exists on the top right hand corner or the upper triangle of the matrix. So a lower triangular matrix, if this is the main diagonal, the only non-zero element that exists would exist in the lower triangle. So this matrix here, B, is an upper triangular matrix. Could it be that E1 inverse times E2 inverse times E3 inverse together would create a matrix that is a lower triangular matrix? As a matter of fact, yes. The product of the inverses of all the elementary matrices created would result in a lower triangular matrix. B is an upper triangular matrix. So what have we really done here? We have succeeded to decompose the matrix A into a lower triangular matrix times an upper triangular matrix, and we call this the LU factorization of the matrix A. Just hold that thought. We'll come back to that later. Theorem. Elementary matrices are invertible. If E is an elementary matrix, then E inverse exists and it is also an elementary matrix. We saw that before. Theorem. A property of invertible matrices. A square matrix A is invertible if and only if it can be written as the product of elementary matrices. That is interesting. So A is invertible if and only if we can write A as the product of elementary matrices. So one question you can be sure you would get is this. If given a matrix A, can you write A as the product of elementary matrices? I.e., find all the elementary matrices such that when multiplied together, it gives us A. And of course, that happens only if A is invertible. If A is not invertible, then we cannot even discuss that. So that is something I would like us to look at a little bit more closely. But before we get to that, let's take a theorem. Equivalent conditions. If A is an n by n matrix, then the following are equivalent. Number one, A is invertible. Ax equals B has a unique solution for every column matrix B. The homogeneous system Ax equals 0 has only the trivial solution x equals 0. A must be row equivalent to the identity matrix In, and we can write A as the product of elementary matrices. Proof. Yes, you guessed it correctly. Left as simple exercises for serious students. But recall, this is what I want you to prove. You have to prove that 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, and 5 implies 1. To prove 1 implies 2 is very easy. Suppose A is invertible, i.e. A inverse exists. Look at the equation Ax equals B. Multiply both sides from the left by A inverse. What do we have? A inverse times A. That crumbles. I end up with x equals A inverse times B, and that is a column matrix. That gives me a unique solution for x, and so on and so forth. Beautiful. Now let me go ahead and just give you this statement, but in lecture 11, I'm going to come back to the concept of LU factorization with some examples. If the n by n matrix matrix A can be written as the product of a lower triangular matrix L and an upper triangular matrix U, then A equals LU is known as an LU factorization of A. I.e., if we ask you to find the LU factorization of A, I basically would be expecting you to reduce A as a product of a lower triangular matrix and an upper triangular matrix. We know how to create the lower triangular matrix. Use your row echelon and get to a row echelon form. Along the way, create your elementary matrices E1, E2, E3, E4, E5, EK. That matrix created, the row echelon matrix created, would be your U. And we know what L would be: the product of the inverses of the elementary matrices. Now, I mentioned something which I said I'll come back to before the close of this lecture. So let me show you something really quickly. Okay, note, as I mentioned before, there would be instances where I would ask you to write an invertible matrix as a product of elementary matrices, and I expect you to be able to do that. Or I may actually ask you to find the inverse of a matrix A using just elementary matrices, or I may ask you to write the inverse of a matrix as a product of elementary matrices, and I expect you to be able to do this with relative ease. Okay, so to find a sequence of elementary matrices whose product is a non-singular matrix A, what we do is we row reduce A to the matrix I, the identity matrix, and we record all the elementary matrices created on the way. Say, for example, I did my Gauss-Jordan elimination and arrived at the row reduced form of my non-singular matrix, which is simply I. Then I would know that E1, E2, E3, E4, multiply all of that by A simply equals I. Now I know that each of these elementary matrices is invertible and their inverses are actually elementary. So I can multiply both sides by the inverses of the elementary matrices to have A equals E1 inverse, E2 inverse, E3 inverse, E4 inverse times I. But since I is the identity matrix, it just falls off and I end up with A equals E1 inverse, E2 inverse, E3 inverse, E4 inverse. What have I done? I have succeeded to write A as the product of elementary matrices. Now I want you to observe something also. If E4, E3, E2, E1, A equals I, then instead of multiplying both sides by the inverses of the elementary matrices, since A is invertible, I can multiply both sides by the inverse of A from the right. So that gives me all of these times A inverse, I times A inverse. But I is the identity matrix, so I times A inverse is simply A inverse. And A times A inverse, which I can freely do because of associativity, would give me the matrix I. So I'm left with E4, E3, E2, E1 equals A inverse, i.e. A inverse equals the product of elementary matrices. This is how we get the inverse of A by using elementary matrices. So if I give you a matrix A and I say find the inverse of A using elementary matrices, what are you to do again? Step 1. Row reduce A to the identity matrix I and record all the elementary matrices created on the way. A inverse would simply be the last of the elementary matrix, one before last, E4, E3, E2, E1. That's all. And if I ask you to write A as the product of elementary matrices, this is what we have. In lecture 11, I'm going to introduce you some more to the notion of LU factorization or decomposition of a matrix. Thank you.